Welcome to Module 1.1 with EF5 training from the University of Oklahoma Hydrometeorology and Remote Sensing Group. My name is Laura Labriola. This is the Advanced EF5 training. If you have not completed the Foundation EF5 training yet, please go back and follow along with those videos. This is EF5 Advanced training builds upon that foundation. So if you haven't looked at those videos, you might be a little lost. So we advise you to go back, learn the foundation, and please come back and watch the EF5 Advanced training. So for today, we'll be looking at ensemble output. We'll be looking at the three ensembles that exist within EF5. They're the Sacramento soil moisture counting model, the hydrophobic model, the CREST, which we've used in the foundation training. We look at model evaluation indices. We look at topographical resolutions. We complete example 1, and then we can practice with calibration. So the advantage of using ensembles is it allows the user to see multiple model solutions for a particular scenario. This example on the presentation shows the different ensembles that exist within EF5. They have the CREST, the Sacramento soil moisture, and the hydrophobic EF5 ensembles. We can see different model solutions and how stream flows can vary within different model physics. Ensembles are a collection of 2 or more forecasts verifying at the same time. The advantage of using ensembles is that it produces a more physically realistic understanding of the Earth's atmosphere and hydrosphere by enveloping a range of possible outcomes. The helpfulness about this is that it aids the forecaster to see all the possibilities of pattern evolution. It can also help forecasters build confidence in a particular model solution. The great thing about EF5 is that it innately has ensemble models with multiple cores that contain different physics to model possible outcomes. The advantage of having an ensemble model is that not every model is perfect. However, using a combination of models may help forecast for a location. EF5 enables ensemble forecasts of hydrologic variables from a single set of input data. This spread amongst ensemble members help enable probabilistic forecasts. The spread amongst members can be achieved in 2 ways. The first is to use multiple hydrologic models that are contained in EF5, and a second is to actually use global ensemble weather forecasts as the forcing. The first method, using ensemble physics cores, will be outlined in this module, while the second method will be outlined in a following module. This schematic is the core of EF5. Right now, EF5 has 3 options for modeling water balance. Water balance models is a topic we talked about in the foundation EF5 training. The 3 water balance that are used in EF5 are CREST, which has been used in all training examples so far, the Sacramento soil moisture accounting water balance model, and the HP, which is hydrophobic. We'll talk about all of these water balance models in the coming slides. We also have the routing models. There is one option for routing with another under development. In all of our examples, we've used the kinematic wave, but there's also the option for linear reservoir, which is still in development. There are 2 other model components. There's a snow component, and there's a simple inundation component. And we will talk about that in this EF5 advanced training presentations. So the 3 water balance models that we are going to be discussing for this ensemble training are CREST, which is a distributed hydrologic model and has been used in all EF5 training so far. we're going to be using the Sacramento soil moisture, which is a continuous hydrologic model, and it's also the soil moisture budget. And then we use the HP, which is no infiltration, and it routes all rainfall downstream using the kinematic wave scheme. And the advantage of this is that it provides a worst case scenario. So you can say it's probably not going to be any worse than this. So these are the three water balance models that we use in EF5. The water balance concerns the water inputs and outputs for each model cell. So if you recall from previous presentations, inputs such as precipitation, upstream runoff, and interflow must be equal to the outputs, which are runoff and interflow to be routed downstream. So we're going to talk about each water balance model in this presentation. The crest param set block in this example is named Greenbrier. And so if you remember from the foundation training, we have the water balance, and then we have the gears that go around it. And as you calibrate these, they can change how your model reacts. We also have the control file to the bottom of the bottom right-hand side, which you can enter values for. The name of the gauge block so we have the gauge, and that's the name of the gauge block to which the parameters apply to. We have WM, which is the maximum soil water capacity. We have B, which is the exponent of the Vic model. We have IM, which is the impervious area ratio. We have KE, which is the conversion factor from PET to actual ET. We have FC, which is a soil saturated hydrologic conductivity. And we have IWU, which is the initial value of soil water, and that's a percentage of WM. These are all of the parameters that were discussed in previous EF5 trainings. If you need a refresher, please go to the Foundation EF5 course. We also have the Sacramento soil moisture counting model, and this has a lot of parameters. It has over 20. You can see an example of how this looks in the control file in the bottom right-hand corner. Because there are so many and such an intricate model, we're going to go into the background about this a little bit more. So this model accounts for all water that enters, that's stored in, and that leaves a drainage basin. And it's a spatially lumped continuous soil moisture model. And we'll talk about these models a little bit more in the next presentation. But these might sound familiar to you because they were discussed in the Foundation EF5 training. The Sacramento soil moisture counting model is ideal for large-scale basins, about greater than 1,000 square kilometers. You can put several inputs into it, including mean precipitation, evaporation, and temperature. The main idea of this model is that the basin is represented vertically by two zones. We have an upper zone and a lower zone. The upper zone is for short-term storage capacity, and the lower zone is for soil moisture and groundwater storage. It uses 6 reservoirs, which are state variables, to represent the rainfall runoff transformation. So the upper zone is made up of the direct runoff, the surface, the runoff, and interflow. The lower zone is made up of groundwater storage and the base flow component of the hydrograph. The last water balance model that is used in EF5 is called the hydrophobic model. And then this is shown in the control file as the HP param set block. We use the gauge to say which gauge we want to apply these parameters to. And it has 2 parameters with it. It has the precip, which is a multiplier of the actual precipitation that occurs. So in this example, we have 5. So we're saying multiply the precipitation that's coming in by 5. And then we also use a parameter called split, which is used for partitioning the water between surface flow and inner flow in the routing schemes. And we can usually leave this at 1. The main point of the hydrophobic model is that there's nothing infiltrated, and then all the rainfall that occurs is routed downstream. So not only does this provide a worst-case scenario, it's useful to diagnose forcing errors in our streams that are regulated. It can also help for urban areas where there's been a lot of precipitation recently. So we can say that there's probably no infiltration going on. So everything that's coming down from precipitation will probably be routed downstream. The hydrophobic model is independent from streamflow observations. So just a quick summary about all those water balance models that we talked about. We've used CREST, which is the coupled routing and excess storage, which has been talked about in the EF5 foundation training. We have the Sacramento soil moisture budget, which we have a paper in the documents section if you need more review about it. And we also have the hydrophobic water balance model that has no infiltration. Just a reminder is that CREST is the water balance model that has been used in all training modules up to this point. So we're going to take a little break from the water balance models, and we're going to talk about calibration. Calibration is the process of adjusting model parameters so that the model can accurately simulate stream flow, and you can compare that to actual stream flow and see how well it correlates. We can adjust each parameter and see how the model evaluation indices change. So if you remember from the EF5 foundation training, we talked about Nash, correlation coefficient, and bias. We'll be reviewing these indices just in case you need a refresher. Calibration can be a lengthy and complex process, and there is no one right answer when it comes to calibration. Automatic calibration is really great, though. However, sometimes we can't always do that. There's 2 ways for calibration. There's something called manual calibration, where you adjust all the water balance parameters individually. So you'll go into the control file and you'll put different values for one parameter and see how that changes your actual hydrograph. However, manual calibration is a time-consuming process that requires active involvement. And using manual calibration, it's hard to know if you actually reach the optimum set of parameters. You may have a good Nash value, but it may be able to be better. However, with automatic calibration methods, it can solve those problems for us by searching the available parameter space using a single objective function and the hydrologic model. So we use automatic calibration in this example. So you can find the full explanation of model evaluation indices in the EF5 Introduction Training, Module 1.3 EF5 Overview, if you need a refresher of how to calculate these model evaluation indices. In this module, we will explain the 3 model evaluation indices and how to calculate them on your own. This module is also accompanied by a presentation and video available online at ef5.ou.edu. So how do you know if your model is actually running well? That's through model evaluation indices. In general, the result is better the closer the match between the observed stream flow, in this case, in the right-hand corner of the figure, the observed stream flow is black and the discharge is red. The discharge is what we've simulated from our model. And we can see how close of a match those 2 are to see how well our model did. But could you tell if the model was better in 2001 or 2002 by just looking at a hydrograph? This is why several model evaluation indices exist. So we'll talk about 3. The first we'll talk about is bias. Bias can be thought of as a shift up or down in a hydrograph. The lower right hydrograph now exhibits high bias. The red line has shifted up. So we have the original hydrograph on the left-hand side, and we introduced bias to it. That means we multiplied the discharge values by a number, and all of the values went larger. So we went from a 32% bias to 164% bias. So it can be thought of as a shift up in the hydrograph. And this is a conditional bias. The higher the original value, the greater the bias. So bias could be constant or non-stationary. And so that's when I talked about it could be a multiple. And so what we did is we multiplied the stream flow values by a number, and they all increased. Usually bias is expressed as a percent. So when bias is greater than 0, the model values are too high on average. So the goal for this model evaluation indice for bias, we want these values to be as close to 0 as they can. The second model evaluation indice that we'll be reviewing is called correlation coefficient. This measures the agreement between the simulation and the observation time series. Measured on a 0 to 1 scale, we want this value to be closer to 1 and far away from 0. So 0 is not desirable and 1 is. And we can think of this as the agreement between the simulation and the observed time series. So if we look at the figures on the bottom, we see that the peaks look pretty well aligned. However, we introduced a phase shift. So we said, let's say we move the time series over a month or two. We can see that the red and the black don't overlap as well. And so we have a lower correlation coefficient because of that. So we think about bias, and it identifies how far vertically displaced the simulation is from the observations. Then we can think of correlation coefficient as measuring the general displacement between the two time series. So this example is highly simplified, but for our purposes and understandings, it works. So the last model evaluation indice that we'll be talking about is called the Nash-Sutcliffe coefficient of model efficiency. And it's referred to as NASH, or written out NSCE. And this exists on a scale from -infinity to 1. When NASH is greater than 0, we can say that the model has more skill than if we just use the average stream flow over the period of the simulation. So usually when it's greater than 0, that's something that we want. That's better than just taking the average of all the numbers. On a hydrograph, NASH can be visualized as the amount of space or distance between the simulation and the observation in a general sense. So now that we've reviewed the model evaluation indices, we're ready for example 1. In order to complete example 1, we're going to have this outline. We're going to ready the control text file for crest, the Sacramento soil moisture, and the hydrophobic. We're going to run EF5 for each of the water balance models. And then we're going to introduce Jupyter Notebook so that we can compare the results for each of the models using a hydrograph that we code ourselves. So before we actually get to all of that, we want to review the EF5 control file. So if it's been a long time since you've watched the foundation training, you can still follow along with us. If you're lost by now, please go watch the EF5 foundation training. So the main point of the EF5 control file is it tells the model what to do. It consists of several blocks, each of which starts with a bracketed statement. These types of blocks include basic, PrecipForcing, PETForcing, gauge, basin, and you can see that in the right figure, the figure on the right. Each block is highlighted around a red rectangle. And in each bracketed statement, the type of block should not be changed. So you'll always have a basic, a precip forcing, a PET forcing, a gauge, and a basin block. However, you can change the name of each block. So in the example on the right, you can change those names of what's highlighted in the red box. So for this example, we use Trim, FuseNet, Chukka, Wang Chu, but that's something that you can change that relates to your basin that you're modeling on. So for just a review of the basin block, or the basic block. The basic block contains 6 pieces of information. We have the DEM, the DDM, and the FAM, and that's the file path to the topographical grids that you've either created or received for the basin that you're modeling. It also contains the PROJ, which is the projection. It's the map projection associated with the topographical information. So it's easiest to use a geographic projecting system with EF5. Finally, there's an option for Esri DDM or Self FAM. These are options related to how topographical information is encoded. If you need a reminder for how this block works, please visit Module 1.4 in the Foundation EF5 training. The next block is the PrecipForcing Block. This PrecipForcing Block is named Trim. The different things to put underneath this block are type, so you want to put the file type of the precipitation. In this case, we're using BIF file, but you might use a TIFF file or other files that precipitation comes in. You'll want to put the units of the precipitation. In this case, we put MM/D, which stands for millimeters per day. You also want to put the frequency at which EF5 will ingest precipitation files. So in this case, we have frequency equals D, which stands for day. But you might have different frequencies for your precipitation files. So if you use Trim, you'll have 3 hours. So for frequency, you'd put 3H. Next is the location, LOC. So that's where the precipitation is actually located. The last thing you need for the precipitation, the PrecipForcing block, is the name of the file. So this is how the precipitation files are named. So in this example, all of our precipitation files are named uppercase TR_2015-0101.bif. So if you look at the control file on the top of the slide, it says name, TR_, which matches ours, and then it has 4 Ys that stand for each component of the year, 2 Ms, which stand for the month, and then 2 Ds, which stand for the day, .bif. If there's ever a problem with this in your control file, and you run the program, EF5 will let you know that it can't find the precipitation file. So you'll have to look back onto your control file and see if that's how, if it matches the name of your actual precipitation files. If you need more review on this, you can visit the EF5 Foundation training. The next block is the PETForcing block. This PETForcing block is named FuseNet in this example. You'll need the type, the file type of the file, which in this case is also BIF. You'll need the unit, which is millimeters per hour. You'll need the frequency of which EF5 will ingest these files, which is every month. You'll need to put the location where the PET is located. You'll need to put the name, and that's how the PET files are named. So in this example, we can keep almost the exact name, but then only change it for the month. So in this case, our file names are PET025.01.bif, where the 01 stands for the month. And so that's how it looks on the control file. We have PET025.mm, which stands for the month, .bif. Something I do want to go over is the location. So if you look at the control file, we see // PT/bibimo. So that's where the files are located. And I'll go over this again when we get to this point. But the // means that it's going back in a directory. So it means we have the control file in one folder, but that's not where the PT folder is. That means you have to go back a directory, and then since we have the // again, it means go back another directory, and that's where the PT folder is. We'll go over this later in the presentation. We also have the gauge block. So multiple gauge blocks can be specified, one for each gauge you want to run the model at. However, for this example, we'll just be using one, and this gauge is called chukka. So for the gauge, you'll need the longitude and latitude. You can also use cell X and cell Y. For longitude and latitude of the gauge, you'll use unprojected and in decimal degrees. Or you can use X and Y coordinates of the gauge in topographical basic files. We'll also need the observations of a stream for the stream flow values. This is required for calibration. However, you don't need it all the time. The water balance models don't use the observations, but you'll want to know the observations so that you can compare to see how well your model ran compared to the observations. We have the basin area, so we'll put the contributing area of the gauge in square kilometers. Finally, we have an option for outputting a time series. So for this example, we put output TS equals true. So we're saying to output the CSV file. Finally, we have a basin block. So multiple basin blocks can also be specified. In this example, we have it called Wang Chu. And then all we have in this basin is one gauge, and that's called chukka. So note that this term for the basin is not a physical basin. Basin here is just a collection of gauges or gauge blocks to be modeled in a single run of EF5. So when you're running multiple gauge outputs, you can actually put basin Wang Chu, and you can say gauge A, gauge B, gauge C. And we can say all of that is in this term basin, even though all the gauges might not be physically in that basin. So looking back into the water balance model, we have many parameters within these. So each component of the model has its own set of parameters. And we can think of parameters are like knobs on a car radio. What that means is that it allows us to tune the model to get better simulations, like how you tune the radio to get better reception. So we talked about these 3 water balance models earlier in this presentation, and we can choose each one to model stream flow with. So we have the Crest water balance model, we have the Sacramento soil moisture water model, and we have the HP water balance model. So in order to run EF5, we'll want to look at the task block. So the task block tells EF5 what to run and at what time resolution. So the task block in this example is named Run Wang Chu. The style is important because it tells the model what type of task it will be completing. Simu is used for basic simulations. So that's the one that we'll want to run to simulate stream flow. You can also tell it which model to run. So in this case, in the right-hand side of the slide, we have model is equal to crest. So in this example, the EF5 will model crest. But you can also use SAC, which is a Sacramento soil moisture counting model, or you can use HP, which is the hydrophobic. For routing, you can use kinematic wave or linear reservoir routing, but since that's still in development, we'll just be sticking with the kinematic wave routing model. And that is denoted by KW. We also have the basin in the task block, which is the name of the basin block over which the model should run. And this should match the basin block that you put earlier in the control file. Next, there's the precipitation, and this should match the PrecipForcing block name. We have PET, which should match the PETForcing block name. We have the output, which is the location where the output should be stored. We also have the param set, which should match the name of the water balance block you create. And we'll be discussing the water balance block later in this presentation. Finally, we have the routing param set, and this is the name of the KW param set block that we will be using since we use kinematic wave. Finally, we have time step, which is the time step used in this simulation. So in this example, we have 1 day. However, if you have precipitation forcing that comes in sooner, like every 3 hours, you'll want to put this time step at 3 hours because you want that to match your precipitation forcing. You also have time begin, and this is the time at which the model starts. You have time warm end, and this is optional, and this is when the warm-up period ends. So if you want to run the model, but you don't want output for the first 4 months, you'll begin it, and then you'll put your time warm end 4 months after that. And then the model will run and output time series after those 4 months. Finally, we have time end, which is a time when the model run ends. So what you'll want to do now is to locate your EF5 Advanced folder. So what we'll do is we'll find EF5 Advanced, which is right here on the screen. We'll go into Examples. We'll go into Wang Chu. And you should see 5 subfolders there. We have the basic folder, which contains topographical data for the model. We have the OBS folder, which contains the observed streamflow for this example. We have PET, which contains the potential evapotranspiration data. And we have the precipitation folder, which contains the precipitation data. Finally, we have another folder, and that's the water balance models folder. And there, in this folder contains the Ensemble configuration files that we will run. So if we go ahead and double click on the water balance models, we'll see that there's 3 subfolders. And each one of these are the water balance models that we've discussed in this presentation. And inside each of these folders is the control file and an output folder and the EF5 software to actually run the model on. So inside each of these folders, we have the control text file, which tells the model what to do. So in the CREST folder, we have one subfolder, the output folder, and we have the control text file. We will review the control file and what inputs we need for the model. So the control text file for the CREST water balance is on the right. We have the basic block, and we have the DEM, the DDM, and the FAM, and they all point to where the files are located. So this part's already completed for you. These files are 2 directories behind the current directory where the control file text is. But we can use ... in front of the folders it is found in to call them in. So for example, we have on our control file, it's saying the DEM file that we're using is in ... basic. So what that means is that we're in this folder. This is where the control file is. So it says this is the main directory we're working in. But if we go back 2 files, so we're in the CREST directory now. If we go back 1 to the water balance, and we go back 1 more into the Wang Chu, this is where the basic folder is. And so once we go into the basic folder, we see that this is where DEM is. So this is where the ... makes sense. We next have the PrecipForcing block, And we have the location for that ready to go with the 2 directories to locate it. We have the PETForcing, and we have the gauge chukka that we will be using. So we're going to talk about setting up model parameters. Each component of the model has its own set of parameters. And as we see, CREST has 13, including the kinematic wave, and the Sacramento soil moisture has over 20. And we talked about how all these parameters allow us to tune the model to get better simulations. So we're going to start with the CREST param set. The CREST param set block in this example is named Wang Chu. And you can look at, we've talked about these parameters in the EF5 foundation training. So if you need a review for those, please go back to that video. For the kinematic wave param set for the CREST, we have the example in the bottom right-hand corner. We have the gauge, which is the name of the gauge block to which these parameters apply. We have TH, which stands for the number of grid cells needed to flow into a cell for it to be part of a channel, and that's called the threshold. We have under, which is the interflow speed multiplier. We have leak I, which is the amount of water leaked from interflow reservoir in each time step. We have ISU, which is the initial value of the interflow reservoir. We have alpha and beta, and those are both used in the equation for stream flow is equal to alpha multiplied by the cross-sectional area raised to the beta. And finally, we have alpha naught, which is the alpha value used for overland, not channel routing. And all these parameters are also explained deeper in the EF5 foundation training. So in this example, we're going to learn how to create a batch file. And this will help you run the EF5 model. So what you can do is you'll go back to your Wang Chu, you'll go back into the water balance models, and we'll go into CREST. From here, we can right-click an empty space, and then you'll go to New, and you'll find Text Document. We're going to call this Run EF5.text. Then we'll double-click and open it up. From here, we're going to type in ... backward slash ... backward slash. We're going to do that 2 more times. So we're going to have 4 of those in total. And we're going to type in software / EF5_64.exe. Make sure you press enter and then write pause. And then you'll want to make sure to enter 1 more time. So from here, we're going to press save. And then we're going to go to File, Save As. So we'll go back into that Water Balance Models CREST folder, and we'll see our output and control file. And we also have the Run EF5.text file. But in order to create a batch file, what we're going to do is change the file name. We're going to keep the Run EF5, but we're going to get rid of the TXT and replace it as BAT. So it should say Run EF5.bat. And the next thing you'll want to do is change Save As Type, and we'll change it to all files. So this is how your screen should look. So we'll press Save. We can exit out of the text file we just created. We can exit out of the control file. And before we run it, I just want to explain one thing. So we typed in 4 of these ... slash into this text file. And the reason we do it is because this is locating where the EF5 software is. And so if you go back 4 directories, so we said if you go back, you can follow along with me on the computer. We're saying go back 4 directories. So here's 1, 2, 3, 4. This brings us back into the EF5 advanced directory. And then it says to go into software. And this is where our EF5 software is. Instead of running batch files, what you can also do is copy this software and paste it into the folder that you're running EF5 on. So if we go back to EF5 Advanced, back to our Wang Chu example for Crest, you can paste the EF5 64 software like it is on here and run it on your own. So now you have 2 options to run EF5. You can run it on this Run EF5 batch file we created, or just simply by double-clicking on the software provided. So I'm going to go ahead and click on the Run EF5 batch folder, and you should see something that runs like this. As we wait for it to finish, you'll get a nice done with an exclamation mark, and the current time set should be the end of your simulated time series. We can safely close out of both of these pop-ups. And we can locate where our output went. So if you double-click on output, you should see that there is a new file there, ts.chukka.crest, and that is your CSV file. Let's see, so we ran it. And then if you look in your output file, we'll see those 2 files, the output from the EF5 model, and then a JSON file. So the next topic that we're going to be showing you is the Ensemble part. So we're going to actually run a new water balance model from EF5. So it's the Sacramento soil moisture counting. So if you go back to your water balance models folder into your SAC water balance, you'll see that you have 2 folders, well, 1 folder, the output folder, and then you'll have a control.txt file. So we'll review the control file and what inputs we need for the model. So we had talked about how we have all of these control file blocks within our control file: basic, PrecipForcing, PETForcing gauge, basin. We have the kinematic wave param set. We're going to have the kinematic wave cali params, which is used for calibration. And then we'll have the task and execute block. And what block do we need to edit? We need to edit the water balance block, because we're no longer using Crest, we're using the Sacramento soil moisture. So as we said, each component of all of the water balance models has their own set of parameters. And these parameters help tune the model to get better simulations. With the Sacramento soil moisture accounting model, it has 23 parameters, which would be really difficult to use with manual calibration. This is an example of all of the different parameters that's involved with the Sacramento soil moisture accounting model, water balance model. So we will go over calibration of Crest, the Crest water balance model, in the next module. However, in this one, we're actually going to calibrate the Sacramento soil moisture accounting model. So we've included 2 new blocks to the control file, which is already on your control file. And you can see it on the right-hand side of this slide. It's called the SAC Cali Params, and then we're putting the gauge that we're using it on, Wang Chu. And then we're also doing it on the KW, which stands for kinematic wave, Cali params. So these blocks work similarly to the SAC param set and the KW param set blocks we are already familiar with. So here are some options we haven't discussed yet that are associated with the SAC Cali params block. We are familiar with gauge. That's the gauge that we want to use with the gauge that we modeled on. But the next new thing is called objective. So So there's 3 possible values for objective. It's the Nash, or NSCE, CC, which stands for correlation coefficient, and SSE, which is the square root of some errors. And each of these seek to improve model performance by improving these measures of accuracy. So in this example, we use Nash. And what it does is that this calibration scheme runs, and it calculates a Nash for each different parameter it randomizes. And if that number isn't very good, it's going to say, okay, let's use a new set of parameters. And if that one has a better Nash score, it's going to keep those. And then it will randomize it again and see if it compares better or worse. So that's why it's important to use this objective. So if you want a high Nash score, you'll use that. The next option is called dream_ndraw. And this represents the number of iterations of dream EF5 will run through before the calibration process is complete. So typically, higher values will take more time, and it may produce better parameter sets. So looking at these 2 calibration blocks that we've created, each parameter line in the 2 blocks follows this structure. We have the parameter, and that we have the parameters equal to a low end of a range, comma, high end of a range. And so to the right of this figure, we can see the control file. And we can see that Dream will only test the parameter UZTWM, which is the first one in the control file. And it only tests those values between 1.0 and 200.0. So every parameter must have a range. We can basically fix a parameter at a value by specifying a tiny range. So if you can find ISU on this control file, which is the very last one, it's 0.0, 0.000001. So we're pretty much saying that that value is 0, and that's how we fix a value. All of these ranges that are on this control file are realistic ranges that you can keep when calibrating your own basin. We also have the parameter values for you on this slide, as well as on your documents folder of your EF5 Advanced training folder. So these are values that are used for the Sacramento soil moisture water balance, the parameter names, the recommended ranges, and a brief description of their sensitivities. So we've already done this for you, but we added a new task block, which is the Calibrate Wang Chu to our control file as well. So you'll need 2 task blocks when running your EF5. You'll have one that's just run the simulation, and this one's going to be running your calibration. So what's changed about this one is the name of it. We've named this one Task Calibrate Wang Chu. What's changed is the style. So if you remember from our simulation, we call that one style is equal to SIMU. However, when you're calibrating, we're going to change it to Cali_Dream. And it stands for calibration_dream because that's the calibration model we're using. So then once you do that, EF5 knows to run in calibration mode. The next line that we add is the Cali param. So this points to the water balance calibration parameter set, which is Wang Chu in this example. The last line that we need to add is called routing Cali param. And this points to the routing parameter set in the Wang Chu in the control file. Finally, we look at the execute block. And we add a new task called Calibrate Okavango. And then we can comment out the old run Okavango task with a # or hashtag symbol. So all you'll have to do is put a hashtag symbol in front of the first one, and that will comment it out. That means the model won't run the run simulation, it will run the calibrate. If you don't have the hashtag symbol on your computer, you can just delete this line or put it after the calibrate Wang Chu. Besides that, we're ready to calibrate. First, we're going to set our dream end draw to 250, and then we'll save your control file. So if we go ahead and go to the water balance models, we'll go to SAC. We'll go to control file. And so we have all these parameters for the Sacramento soil moisture. We have our parameters for the KW param set. Here are our calibration ranges. You already have it to 250. We have the kinematic wave parameters that are already set for you with ranges. So we have the two task blocks. We have the run Wang Chu, which is a simulation. This also uses a SAC model. But what we want to do is calibrate. We don't know what values are good. And since there are so many parameters, it's hard for us to manually know which ones are the best values to simulate streamflow. We have our calibrate Wang Chu task, where we use the style Cali Dream. We use the SAC model. We use the KW routing model. And then we've already commented out the run Wang Chu, so it will run the calibrate Wang Chu for us. So you can either create a batch file or you can paste the software. In this case, I'm going to run the software, and you'll see it does the same thing. Important point to note is that it says warning, failed to load preload file output / Cali forcing spins. You don't have to worry about that warning. What that means is that we've never run this calibration on this data set before. So that means it didn't load the preload file that's created. Once you run this simulation or calibration, it will create a preload file for you. So if you ever want to run it again, that file already has the input forcings that you need already stored, so your model is going to run a lot faster. So this will take you about 15 minutes to run. However, we've included a calibration for you that iterated 2,000 times already. So we'll go ahead and explore that file. Okay, so we have each column represents a different parameter value. However, if we scroll all the way to the right, to column AD, it says Nash. So our first Nash value for a randomized set of parameters was -6. And we said that anything less than 0 isn't as good as just using the average streamflow values. So that's not very good. But as we scroll down, as we get further into the calibration scheme, we get closer to 0, then we get above 0, and if we scroll all the way down to the 2,000 iterations, we get a Nash score of about 0.62, which is a pretty good score for Nash. So that means we had to run this calibration scheme 2,000 times to get a pretty good Nash score. The importance of this is that it shows you, it outputs all of the terms for you. So we have all of the calibrated water balance Sacramento soil moisture counting parameters right here in the Excel file. So what you'll want to do with that is go to your Sacramento soil moisture folder. You'll double click on control, and we'll go ahead and replace the values that are in that control file with the ones that are on here. And as you can see, we've already done that for you. So these values were the ultimate values that you could have picked that gives you the best Nash values. So what you would do is you would highlight just on this A column, and as you can see, it already gives you the coding that you would put in your control file. So what you would do is you click on the A 2004, And you can hold down your mouse and scroll all the way down until you get to routing. So you don't want to highlight routing. You'll copy this. You'll go to your control file with the Sacramento param set. You'll want to make sure that you're putting it in your Sac param set control file. There's a different block called the Sacramento Cali params, the Sac Cali params, and those have ranges. These are just for your calibrations. So when you have the solid value, when you actually have this value is equal to 3.4, you don't want to put that in your calibration control block. You want to put that in your Sac param set. These have the solid numbers that you want to run the simulation with. So we'll go ahead and highlight all of these that we want to replace. Then we'll press copy. We can delete it first. Let's see. We'll keep gauge. So you'll delete it, and then we'll paste all of the numbers from our Excel file. And you'll do that with the KW param set as well. So I'll go ahead, go to A2027, all the way down to 2033. Press copy. Go back to our Excel file or to our control file. Highlight everything from under to alpha naught. We'll press delete, and we'll press paste. So that should be under your KW param set Wang Chu. So now we got the best values for our Sacramento soil moisture counting model. And we got a Nash of 0.6. So if we were to simulate this model, we would have a pretty good simulation for this time range. So there you have it. You calibrated the Sacramento soil moisture parameters that has over 20. And we did that. We got a pretty good Nash in just a few minutes. Finally, the last water balance model that we're going to be looking at is the hydrophobic. So this only has 2 parameters, so it's not too difficult to model. It has the precip, which is that multiplier that we talked about, and then it has this one called split, which is used for partitioning the water between surface flow and inner flow in the routing schemes, and we just leave that at 1. So we don't actually have to calibrate this model at all. It doesn't need observations. It just takes in the precipitation, and it just routes it all downstream. So we'll go ahead and go to we'll navigate back to our EF5 Advanced folder. We'll go into Examples, Wang Chu, the water balance models. We'll go into HP, and we have the output folder there and the control file. We'll go ahead and open the control file, and we see all of the regular blocks that we're familiar with. But we see this. This is different. This is called the HP param set. So this is for the hydrophobic parameters. So we only have the gauge, the precip, and the split under this. We still have our KW param set. And then we've also changed it in the task run Wang Chu. We say model is HP. Okay. And we have task run Wang Chu. So we'll want to paste the software. So we'll have to go back into EF5 Advanced to software, copy it in. Go back to Examples, Wang Chu, water balance models, into our HP. We'll paste that. And then we can go ahead and run our model. And it's already finished. So there you have it. You were able to run all 3 models. You calibrated the Sacramento soil moisture counting one, which is difficult to do since it has so many parameters, but we were able to do it in just a few minutes. So now we're going to move on to interpreting results. In our last training, in that EF5 foundation training, We use Excel to calculate the model evaluation indices on our own, and we use that to create hydrographs as well. However, in this training, we will be using computer programming to create a hydrograph and produce the model evaluation indices. An example of that is on the bottom of this slide. So you'll have to do this on your own, so you might want to pause the video and look at the presentation to sign up for an account. But the first step you'll want to do is sign up for a Microsoft account. In order to do this, you'll go to the notebooks.azuri.com website, and you'll press sign in, which is in the top corner. So if you go ahead and go to your internet, you'll go to Azuri. You'll go to notebooks.azuri.com. And I'm already signed in, but you can see there's a sign in this corner. You'll press sign in with account. You'll say no account, create one. Or if you have your own Microsoft account, you'll sign in with that. Or if you have your own account on here, you'll just enter your own credentials. If you don't have one, you'll go ahead and create one. You'll then have to locate verification emails in your personal mailbox that you signed in under. You'll enter that number into the browser and click yes for the notebook to access your info. And you can follow these steps with the pictures at the bottom of this slide. Once you have that all programmed in, you're able to log on, you're going to visit this website. Let's see. It's github.com/hydroslab/EF5-analysis. You'll scroll down on that page and you'll see something called the Jupyter Notebook for plotting EF5 hydrographs. Okay. So if you go to the GitHub website, you'll go ahead and scroll all the way down. And you'll see this thing called Jupyter Notebook for plotting EF5 hydrographs. And you'll click on this black and blue box. You'll go ahead and press import. And you'll press import again. So it already existed with mine, but this is how you would do it. And that would take about a second or a minute, depending on your internet speeds. Okay, once you've finally caught up, we're gonna look at what we have in front of us. So I'm gonna go ahead and click EF5 analysis, and you should have something that looks just like mine. We have the EF5 analysis.ipymb. That stands for a Python notebook. So, and we can see in file type it says notebook. We also have something that is called the EF5_stats.py, and that's actually Python code that is used in the Jupyter Notebook that we'll be using. The README is information about the stuff that we have on this notebook. And we also have a CSV file to show you an example. So we're going to go ahead and click EF5 analysis.ipymb, and a new window will open up. So we're going to click this EF5 analysis.ipymb, and this is our Jupyter Notebook. And it might take a minute to load. So now that we're in our Jupyter Notebook, we see the title slide of this is called EF5 Output Analysis with Python. So we're going to be using Python code to actually look at the hydrographs and the model evaluation indices with the Jupyter Notebook. The first line says matplot lib inline, and that's just a coding in Python you don't have to worry about. The next line is called from EF5_stats import make stats plot parse date. And so that actually comes from the EF5 stats Python code that we saw that's in that file in the EF5 analysis. So if we go back to that main page, we see a a code that says EF5 stats.py. And if we actually look into it, it has all this coding already in it for you. So if we go back to our Jupyter notebook, what that is, it's calling that code and saying import these two libraries. And it's called make stats plot and then parse date. So you'll see these two lines of code come up later. So the next part of this Jupyter notebook is called let's make a time series plot of the full time series. So we use this code called make stats plot. We have parentheses, and the first part, it has the time series that we upload. So in this case, in our main Microsoft Azure homepage, in our HydroSlab EF5 analysis, we have the file ts, which is time series.nazoya.crest.csv. And that needs to match the time series that we put into this code. And with apostrophes or quotations. Next, we're going to put a comma, and then the next part of it is the title of the figure that you want to name. So in this case, since we're doing a Nazoya time series, we're calling it Nazoya EF5 example. In order to run this code, we need to run it. So what you'll do is you'll click on the first line, and you'll press run. And you'll see a star popped up, and so that means that it's running. So once one popped up, we know that it's fully run. Next, we can run the second line, the make stats.plot. So we'll go ahead and press run, and a star will come up saying that it's going to run, and then it pops up. So let's talk about what we just produced. So what we produce is a hydrograph. We have precipitation on the top axis. We have the time in the x-axis, and we have discharge on the primary y-axis, and then we have the basin average rainfall on the secondary y-axis. And we did this when we did the foundation training, when we would create hydrographs to the Excel document, but here it's already automated for us. We took the output from EF5, that time series, and then we coded it so that we can make a pretty hydrograph that also shows us the model evaluation indices. We can find the model evaluation indices in the top left corner of the hydrograph. For this simulation, over 3 years, we had a Nash of 0.15, which is a little bit better than 0. However, we would need to do more calibration on this basin to get it for an operational forecasting. We have a bias of -29, which isn't too bad. It's pretty close to 0. And we have a correlation coefficient of 0.58. We would like this number to be closer to 1, but it measures measures the peaks and the pretty well. The next part of the Jupyter notebook is zooming in on a specific period in the time series. So this has a little bit more coding into it. We have it says make stats plot, like the first one, where we input the time series CSV file that we're looking at. The next is the title, which we put earlier. Now we put another comma, and we have start time is equal to parse date. So what it does is that it takes your CSV file and it changes the date around so that we can put it pretty on the figure. So you enter the date that you want. So in this case, we want to look at 2004. And we're looking at April, May, and June. So that's why we called it Nazoya 2004 AMJ, April, May, and June. We put the start day in April 2004, and then we put the end time in July. So we could go ahead and just run this code. And we have our output. We have Nizoya 2004 for ANJ, April, May, and June. And we can see how well our simulation, which is the blue line, correlates with or how well it matches with the observations, which are the dots. These model evaluation indices aren't as well as it was for the whole time series, but with calibration, hopefully we would be able to get better estimates for this. So now that we've seen how these Jupyter notebooks work, we're going to go ahead and try our own input. So we're going to need to we can exit out of we can just go back to our Microsoft Azure Notebooks web page where we have all these files that we looked at earlier. What you're going to do is press this plus sign for new, and we're going to go to computer. So from here, we're actually going to go to choose files. We're going to navigate to our EF5 Advanced, Examples, Wang Chu. We're going to go to the Water Balance Models. We're going to go inside CREST, into the Output folder, and we're going to use this time series to see how well the CREST model did. So we're going to go ahead and press Open, and you should see it pop up here, and we'll press Upload. So now we have our Chukka CREST time series that we produced on our own in the homepage of the Microsoft Azure Notebooks. So we're going to go back to our Python notebook where all our plots are. And what we're going to do is we're going to rename this time series. So we're going to have it match exactly to what we have in our on this page. So what you can do is you can either remember how it's spelled, or you can right-click, press Rename. You can copy it using Control-C. You'll click out of it, so you'll keep the name. And then you can highlight Nizoya, delete it, and then paste the actual name of it. Let's see. Oh. So you'll want to delete everything between the apostrophes and then press paste. And so since this isn't an example anymore, this isn't Nizoya, we're going to put Wang Chu, EF5 hydrograph. Since we've already run this first piece of code, we can go ahead and just press Run on our line 2. And our Wang Chu example is uploaded. We can see that the simulation matches the observations pretty well for just a dry run. We have a Nash value of 0.74, which is pretty high. It's a very good score. We have a bias of -10, which is really close to 0. And we have a correlation coefficient of 0.87. So overall, we made a great simulation with EF5 for this simulation run. However, we can also look at how it does for a specific period in the time series. So we can see from our hydrograph that there's a high precipitation event between June, July, and August. So we're going to input that into the next line. So we're going to have to edit this code a little bit. We're not going to use the Nizoya time series, so we're going to delete everything between those quotations. We're going to put in the new time series that we're using, ts.chukka.crest.csv. We're going to change the name of it. So this Wang Chu precipitation event was in 2002. So we're going to name it Chukka 2002 JJA, which stands for June, July, August. We're going to change this date to 2002. '06. And then we're going to change the next one to 2002. And since we're doing it to the end of July, we'll change this to August so that it will stop on August 1st. Okay, so it looks like we have everything right. We'll go ahead and press run on the top. So we zoomed in on 3 months, and we can see that the observations matches up with the simulations fairly well. Our Nash went down a little bit to 0.48, but that's still a great score. We have a bias that's even closer to 0, and we have a correlation coefficient of 0.77, which is still really good. You should go ahead and simulate your Sacramento soil moisture and your hydrophobic model results on your own. So we're going to talk about the best uses of each model. So we've talked about 3 water balance models during this whole presentation and the different ensemble outputs that EF5 can use. However, when do you know when it's best to use each of these models? We know that each water balance model contains different physics cores that dictate how well it will model stream flow. Different basins will work better with one model over the other, but it's up to you to determine which model is best using those model evaluation indices. So in summary, what we did for this presentation is that we reviewed all the water balance models that is available in EF5, which are the CREST, the Sacramento Soil Moisture Accounting Model, and the hydrophobic model. We edited the control text file and learned all the different ones for all different water balance parameters. We calibrated the Sacramento Soil Moisture Accounting parameters. Since there were so many, we had to automatically calibrate so that we wouldn't spend days or weeks or years calibrating just one model. Finally, we produced and analyzed the EF5 output with model evaluation indices through computer programming. We were able to use Jupyter Notebook to press run and create a beautiful hydrograph and calculate the model evaluation indices almost instantly. So thank you for joining me for Ensemble outputs with EF5. Our next module is distributed parameters. If you can find it in your EF5 Advanced Presentations directory, thank you very much, and I hope to see you during the next presentation.